So we're going to dip our toe into electrostatics, static electricity, charges that aren't allowed to move. And then in the second half of this unit, we're going to say, what if we let the charges move through wires? That's what circuitry is. We're going to start off very basic. Matter is made up of atoms. This is the Bohr model of an atom, which isn't accurate, but it's okay. So we like to think that an atom has a nucleus in the middle with protons and neutrons and electrons. Even the word orbiting has fallen out of favor now because orbiting suggests that they're circular orbits and that they're moving in a circle. They're not, Ella. They're doing much more weird than that. Now we like to talk about energy levels or electron shells, but this will still work for the purposes of what we're doing. And it turns out when atoms bond together to form solids, they can be tightly bound to the atoms, as in covalent solids like glass. These materials are called insulators. They don't transmit electricity very well. They let charge build up, but they don't let it go anywhere. They can also be free to move around, as in metals. These will be called conductors. So most metals are very happy to pass an electron from one atom to another atom to another atom to another atom. And it turns out subatomic particles like protons, electrons, and neutrons have a property that we call charge. And it is this thing called charge that's responsible for both electricity and magnetism. It turns out we should really say electromagnetism. It's one force. Some basic facts about charge. You might know some of this, but this might have been interrupted because of your COVID experiences. There are two types of charge that we call, anybody know? You kind of know this because you know what protons are and you know what electrons are charged. Eric. Positive and negative. My abbrev for the word positive is a plus sign with a VE. My abbrev for the word negative is a minus sign with a VE. If I just see a plus sign, I think I'm missing an equation. If I put the VE, then that's the word. That's my stupid shorthand. You can use whatever you want. Positive and negative. Does anybody know what the correct units for charge are? Charge is measured in coulombs, and the abbrev is a capital letter C, named after a scientist whose last name was Coulomb. In fact, today's lesson is we're going to be looking at Coulomb's law. Mass is represented by the letter M. Speed, velocity is represented by the letter V. What abbrev do we use for charge? You might think, how about the letter C? Lowercase c is already taken for the speed of light. Uppercase C is actually something different. And so we use the letter Q for a big charge or lowercase q for a tiny charge. In the same way I did big M and little m, you're going to start to notice there's a lot of mathematical similarity between how charges exert forces on each other and how masses exert forces on each other. Why Q? It's a good question. Another very important fact about charge is that, here's your word, it's quantized. And yeah, Marcus, that's where the word quantum physics comes from. What does quantized means? It means that it comes in a fundamental smallest chunk. Our money is quantized. The smallest unit of money in the North American and the Canadian system is the penny. If you go smaller than the penny, we don't allow it. You automatically round off to the nearest penny. Okay? All of our other amounts are numbers of pennies, are adding up a bunch of pennies. There is also a fundamental charge. So with money, there is the smallest unit, the cent or the penny, and any unit of money, any amount of money can be broken down into a certain whole number, capital N, of pennies, but never a fraction of a penny. With respect to charge, the smallest unit is called the elementary or fundamental charge. It's on your formula sheet. Go find it, please. Its symbol is lowercase e, not for electron, but for elementary charge. How big is the elementary charge, Victor? It'll be in the same section as all the constants and radius, that one there. What is the elementary or fundamental charge? I think it starts out as 1.6. Okay, now you know where in that section where all of the data is. 1.6 times 10 to the negative 19 coulombs. You'll probably end up memorizing that, but if not, it's on your formula sheet. All other charges are multiples of 1.6 times 10 to the negative 19. In other words, if you want the total charge, it's some number times E. Or if you want to know how many electrons or how many protons, it would be the total charge divided by the elementary charge. You can actually figure out how many extra protons or how many extra electrons. The charge on a proton and the charge on an electron is the same. A proton is positive 1.6 times 10 to the negative 19 coulombs, and an electron is negative 1.6 times 10 to the negative 19 coulombs. Is that big? No. Right? Technical comment. This is already out of date. After we defined the elementary charge as 1.6 times 10 to the negative 19 coulombs, we found that there were objects called quarks that had smaller charges of 1/3 E or 2/3 E, or negative 1/3 E or negative 2/3 E. Arian, we're going to pretend quarks don't exist. Okay? They do, but this will work if we just pretend they don't exist. In this course, you're going to get a data page or formula sheet. You probably saw it already. So on there, you should see in that section the elementary charges there of 1.6 times 10 to the negative 19. You should also see the mass of the electron is there. Yes, 9.11 times 10 to the negative 31. The mass of a proton, 1.67 times 10 to the negative 27. Mass of a neutron, I might not have given you that. We don't use neutrons much because they're neutral. They don't interact that much. So did I give you the mass of a neutron? No. If you need it, it'll be given to you in the question. What you will need to memorize is this. So the data page doesn't explicitly list the charges of the particles, so you'll need to remember the following. Electron, our abbrev for an electron is a lowercase e with a minus sign. Its charge is negative 1.6 times 10 to the negative 19 coulombs. A proton, our abbrev, is often a lowercase p with a plus sign as an exponent. Its charge is positive 1.6 times 10 to the negative 19 coulombs. Our abbrev for a neutron is lowercase n with a 0. What's the charge on a neutron as a number exactly? It's the reason it's called a neutron. 0. You will need to know those, but I'm hoping you've picked that up in your science and chemistry courses. All right. Turn the page. Although this does not need to be memorized, you may have run, or you may have seen from Science 10, now your Science 10 was interrupted by a pandemic, but you may have seen that an alpha particle, symbol alpha, is a helium nucleus. It has 2 protons, 2 neutrons, and no electrons. What's the charge on this particle? Well, 2 protons would be 2 times 1.6 times 10 to the negative 19, plus 2 neutrons would be 2 times 0, plus no electrons. I think it's going to be 3.2 times 10 to the negative 19 coulombs. So Arian, if you know the charge on an object, if it's positive, you can figure out how many extra protons it has. If it's negative, you can figure out how many extra electrons it has. For a conductor, which we'll look at in a couple of lessons, electrons flow easily and freely. But for an insulator, the electrons cannot flow, but they can shift slightly. This is a phenomenon known as polarization. We'll talk about that in a second. But here is the key idea. Electricity, electromagnetism, Dean, it's one of the 4 fundamental forces. Charges exert a force on each other. And this part you will need to memorize. It says fill in the blanks. Like charges will something, unlike charges will something. What do like charges do? I'm looking for a word that starts with letter R, and then an E, and then a P, and then an E. Sorry, what was that? Joanna, like charges what? From that alone, you can explain an awful lot about the universe. Oh, and unlike charges, Will, so if I was going to draw the direction of the electric forces in these two electrons, they would repel each other. The bottom electron would feel a force down or south. The top electron would feel a force north or up. What about here? Well, this proton would be attracted to this electron. This electron would be attracted to this proton. One of the safest places to be during a lightning storm is inside a metal car. Why? How come? Marcus, what do you think? Because it's grounded? I don't think it's grounded. Many people will say, oh, Mr. Dueck, it's because the tires provide insulation. That's nonsense. The lightning has just leapt a kilometer from the sky to your car. I assure you the charge can carry on and continue the 30 centimeters and get to the ground. Okay? Does anybody know why a metal car is so good to be in? Pardon me? Why is being inside a conductor so good? Joanna, like charges? That's going to be your cue for a while, so I'll be coming back to you. That'll be your line. Remember, there are no small parts, only small actors, so you've got your part. Like charges? Okay. Suppose the metal car absorbs 1 billion electrons, or gives off 1 billion electrons, because lightning can also jump upwards. Lightning can be both positive or negative, depending on the circumstances. But let's pretend it's absorbed 1 billion electrons. Like charges? What's the easiest way for the electrons to repel each other? They're stuck on the car. They can't leave the car. Where will they go? They will go all around, spread out evenly, the outside of the car. Where are you sitting? The inside of the car. Okay? So this comes out of like charges repel and the fact that a car acts like something that we call a Faraday cage. A Faraday cage is a metal cage, and you're safe inside a metal cage. It's very counterintuitive. People would say, why would you want to be inside a metal cage around electricity? Because like charges, the charges will gather on the outside of the cage. You will be on the inside of the cage and just fine. We'll write that out in just a second, but put your pencils down and look up.
Did you know that in this country, more people are struck by lightning than are crushed by reptiles or injured as the result of a prolonged stay in a weightless environment? Yeah, it turns out lightning really is a hidden menace. Your point being, well, this. What happens if you're struck by lightning in a car? Oh, you'll be all right because you've got rubber tires. Not necessarily, you see, because car makers don't test for this sort of thing. So, after being pelted by golf balls, Top Gear arranged for a car to be struck by lightning, with me in it. There are very few places in the world that have the technology to blast a car with lightning. Places are in Holland and Germany. But only one of those nations is laid back, liberal, and fun-loving enough to let me actually sit in the car whilst they hit it with 800,000 volts. Yep, it's those zany Germans. This is the Siemens High Voltage Lab in Berlin. Normally, this place builds and tests high voltage equipment for power stations and the national grid. These transformers can generate almost 2 million volts of pure electricity. But today they're going to use that electricity for something else, to make lightning. They're going to zap me and this car with 800,000 volts, which is a lot. Stuff in your house runs on 240 volts. If it
120 volts in North America.
hits me directly, they'll clean me away with a shovel. You might be thinking that the tyres are going to protect me by insulating the car from earth because they're rubber. Electricity can make it from the sky to the car. It can make it from the car to the ground. What's going to protect me is this, the body shell itself. Like all cars, the new Golf's body forms a Faraday cage. And a Faraday cage is something that attracts electricity and then sends it shooting around the outside so that whatever's inside shouldn't be harmed. But the problem is, this isn't like brakes or airbags. Car firms don't test for lightning strikes, so I've no idea how to go. Right. My life is now in the hands of alien physics. The lightning will come out of these transformers along the wires and then shoot down to the car. Starting to raise the voltage. 100,000 volt. A briefing with the scientists, and he said, keep my hands together towards the centre of the car and away from any metal objects. But it's a car. It's made of metal. 400,000 volt. I can hear a noise. I can hear a buzzing there. I can almost feel the tension. Oh, now it's doing stuff to my car. I've got error up on the dashboard. Handbrake light flashing. So it works. Assuming I'm not now talking to you with wings and a heart, I'm alive. Question is the car? Well, the electric windows work, obviously. Lights, they work. Stereo, it's nice. Indicators, I mean everything. And it starts. It still works. Amazing.
All because like charges repel. So, like charges repel, the charges gather on the outside of the car. And you are on the inside. Does anybody remember the name of this? What kind of cage? This is good nerd trivia, but you'll also see Faraday cage. I will go on my Michael Faraday rant one day, but not right now. One of my nerd heroes. The father of electricity, basically. It's why people that work on power lines, they wear metal-lined suits. Example 5. A negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Explain why this happens. Let me pause the video for a second. We're going to use something called a charge diagram. Now, we should point out a charge diagram, it can't show every charge because there was probably billions of electrons involved in what you just saw. Can I draw billions of electrons? No. Here's what I'm going to say. This rod was charged negatively, and this ball was neutral. It had, let's say, 2 negatives and 2 positives. Two billion negatives and 2 billion positives. Right when they touched, what happened? Well, those 2 positives were attracted to the negatives in the rod, and the negatives were repelled. So for a split second, the side that touched that little wand, that magic wand, but we think that's the origin of magic wands, by the way, was charged sticks, because you can see I can make something move without touching it. The one side of that ball was charged positive. And what quickly happened then is some of those electrons jumped the gap because they wanted to get near those positives. So now, instead of 2 electrons and 2 protons, maybe I have 4 electrons and 2 protons. Now, Kenta, what's the charge on the ball overall? Is the net charge positive or negative? Now it's negative, and now like charges okay. This is charging by conduction. What does conduction mean? We came in physical contact, and charges were actually transferred from one object to another. When I used to teach Science 9, I would always tell kids conduction requires contact, if you're looking for a dumb way to remember. You don't have to have contact. There are many ways to induce a charge, charging by induction. If any of you have a charging pad for your smart device, for example, or if any of you have an electric toothbrush, all of those are charging by induction. And there's various clever ways to do it, but here's a fairly basic way. It says this, example 6, 2 uncharged metal spheres are fixed onto supports and they are touching. Right now they're neutral. So we'll say 2 electrons each and 2 protons each, 4 and 4. A negative rod is brought into place nearby but doesn't touch. I'm going to bring a negative rod in. What's going to happen? Well, like charges, unlike charges attract, all of the positive charges are going to move closer to the negative rod. All of the negative charges are going to move away from the negative rod. And now I grab the base of the right-hand sphere and I just slide it sideways, keeping this rod in place. Now you notice I haven't touched the spheres with the rod, but now if I move these apart, I still have the same situation as before. But now I move the rod away, and Victor, what I have done is I have charged both of these spheres, one positive and one negative, and I didn't actually touch the spheres. I didn't transfer charge from this wand, from this stick to the spheres. I just rearranged the charge within them. So there is a way that you can charge an object without touching it. There are many more clever and ingenious ways, and that's becoming more and more the trend. So I have an older smartphone. My iPhone is an iPhone XS or XR. I can't even remember. Most of the modern ones now, I think you have a little pad you put it on to charge up, right? You don't plug it in anymore. So like charges, that means they're exerting a force on each other. And here is the equation for the force. This is on your formula sheet, although you might end up memorizing this. I'll use a lowercase e for electric force, equals K Q1 Q2 over R squared. What does this equation look really similar to? This should look kind of similar to something we just did. What? Yeah, it's very similar mathematically to universal gravitation. And in fact, the mathematics of both phenomena are the same. Masses radiate out gravitational fields in all directions, like the tentacles of an invisible octopus. Charges radiate out electric fields in all directions, like the tentacles of an invisible octopus. Mass is the equivalent of, or charge is the equivalent of mass for electrical force. Charges create electrical force, mass creates gravitational force. Oh, we once again have a constant, so instead of big G to get an answer in newtons, we have lowercase k, and that's on your formula sheet. Probably right around where the elementary charge and the mass of the proton and the electron is. Eric, what is lowercase k? It's 9 times 10 to the ninth, which is much nicer than 6.67 times 10 to the negative 11 to type on your calculator, because you'll find, oh, 9 scientific notation, 9, you just boom, boom, and it's really, really quick to type. 9 times 10 to the ninth. What did I call it on your formula sheet, Eric? Constant in Coulomb's law. Okay, it doesn't have a name. Times 10 to the what? What was gravity? Times 10 to the negative 11? That's 10 to the 20th difference. I told you the other day that electricity is far stronger. Electric force is definitely way stronger than gravity. Okay? Charge 1 needs to be in coulombs. 1 coulomb of charge is huge. If you absorbed 1 coulomb of charge, it wouldn't just be you're dead. It would be the horror movie electrocution death with smoke and melting and okay? So we're typically going to be doing charges in micro coulombs. A micro coulomb is a reasonable amount of charge to be moving around. Gravity, we didn't have a problem figuring out the direction of the force. It was always toward the center. But we've got a bit of a problem here. Joanna, like charges can, stuff can fall up. Really, is kind of what we're saying. So to find the direction of the force, we use like charges repel and unlike charges attract. Put your pencils down, look up.
Electrostatic.
So this is a YouTube channel called Electro Boom. Some of you may have seen his stuff. He's local, by the way. He's from BC. He has his master's in electrical engineering. He deliberately gives himself shocks for entertainment, but also to educate. He very much knows what he's doing. Do not try and recreate the stuff that he does. He absolutely knows how big a shock he can handle or how big a thing he can spark. Don't try it yourself. This is one of the first videos he puts out because he often likes to play, early on, he liked to play a bit of a bumbling fool because he knew that would get him views. He really knows his stuff. So.
Hi. Electrostatic discharge, or ESD, is an electrical charge that is stored in something like human body and can jump to devices like laptops and cell phones and everything. So engineers do a lot of testing on these devices to make sure they won't fail. What they use for testing is something called an ESD simulator or a gun. Here is a 25 kilovolt discharge to a grounded box.
Why didn't he get a shock? The box is grounded. Electricity will typically follow the path of least resistance. Your skin is actually a pretty good insulator. It has a fairly high resistance. And so you actually get shocks all the time without noticing it. The charges just flow on the outside of your skin. They never penetrate your nervous system, and they just discharge when you touch something else. You're getting shocks all the time. It's when they build up. That's when you get a spark or a little owie, owie, owie. So no shock there.
The tip of the gun here simulates a human finger. Always be careful with your tools. Now, they usually zap a completely assembled unit. But sometimes it's also beneficial to zap a better board like this one and see what happens on the actual board. Never hold the board you're zapping with your hand because the ESD will jump to your body through the board. Now this board is connected to ground with this wire, so if I try to zap it, it will continuously discharge. But if I disconnect the ground wire, it will only jump a few times. Because now the board is charged to the same level as the gun and it doesn't jump anymore.
So that board is sitting on styrofoam. It's just absorbed a bunch of charge, and because it's sitting on styrofoam, it can't go anywhere. There is a bunch of charge stored in that board. So when he touches it, what's going to happen? Okay? He knows what he's doing.
How will this charge go before touching it?
Later on today, I will give you an opportunity to experience voluntarily the biggest shocks of your life. We'll get there. To solve force problems, first thing, we have to express charges in coulombs. You're going to see in the homework, it's often microcoulombs. Then we substitute charges and distance into Coulomb's law to find the force, Hannah. And then to figure out the direction, we use like charges and unlike charges attract. Little technical comment. If you have unlike charges, for example, one's negative and one's positive, then the answer that you get will be negative. A negative really means opposite charges and a force of attraction, but it's not a negative force. And so many textbooks will simply put absolute value signs around the Q's. Did I do that on your formula sheet? I know I've thought of, okay. So you don't put the negative or positive into the equation. The force will always be positive, Fahim, but you'll figure out the direction by using like charges and unlike charges attract. Okay? Example 8, find the electrostatic force on the electron in a helium ion. Okay. Brandon, what does this want me to find? Fe. Fe equals K Q1 Q2 over R squared. I think R is pretty obvious. What are the charges in this question? I think we have the nucleus. What's the charge in the nucleus, Brandon? What does it say in the picture? To what? What do the N's stand for, first of all? Do we care? No. What do the P's stand for? What's the charge on one proton? Your hint is it's pretty elementary to figure out. Okay, so let's plug in our numbers here. K is a much nicer constant, 9 times 10 to the 9th. 2 protons is going to be 2 times 1.6 times 10 to the negative 19 coulombs, 2 elementary charges. And then on the electron, it would be 1 electron. What's the charge on an electron? Your hint is it's pretty elementary to figure out. Technically negative, but are we going to put the negative in here? Nope. We'll just know that it's being attracted. Okay, 1.6 times 10 to the negative 19 all over 2 times 10 to the negative 11. Hey, don't forget the squared. You want to practice these on your calculator. What do you get? I got 1.15 times 10 to the negative 6. Is that right, or am I wrong? Yeah? Brandon, units, it's a force? Yep. Is that a big force? It's massive. Relative to the electron. Let's find the acceleration. If F equals ma, how would I get the a by itself? Everybody on your calculator, go answer button divide by the mass of the electron. It's on your formula sheet. I know it's 9.11, but I can't remember the 10 to the. What is the 10 to the? Negative what? Negative 31? What's the acceleration involved here? And the answer, this is what I'm telling you. In terms of the electron, that is a massive, massive force, gargantuan. That's a crazy acceleration. Okay. Oh yeah, I even wrote that. I said, although the force you calculated may seem very small, we should note we are dealing with electrons which have a very tiny mass. If you find the acceleration on the atomic scale, Again, Victor, that's a huge force. I like example 9. I like example 9. I like example 9. Example 9 is a nice question. It says, find the net electric force and direction on the positive 1 microcoulomb charge shown below. All right, some advice. Aiden, how many charges are there in this picture? Be obvious, there's circles. Okay, ready? Let's try that again without the hesitation. How many charges are there in this picture? Anytime you get a charge picture, if they haven't done it for you already, label them. I'm going to call this one Q1, Q2, Q3. Do yourself a favor. And so now, Aiden, I'm going to ask you, which charge do they want me to find the net force on? Q1, Q2, or Q3? Read the question and figure it out. They want me to find the force on Q2. They don't want me to find the force on Q1. They don't want me to find the force on Q3. Well, Q2 is feeling force from 2 other charges, Q1 and Q3. Got the argument? So here's what we're going to do. We're going to find the force on Q2 from charge 1. That's going to be K Q1 Q2 over R squared. We're going to find the force on charge 2 from charge 3. This is my high-tech abbrev. That's going to be K Q3 Q2 over R squared. We'll figure out the direction by using like charges, unlike attract, and we'll add them vectorially. Since they're in a straight line, we'll probably just go who's winning, winner minus loser, or if they're in the same direction, winner plus winner. So Aiden, let's do the first one. What's K? 9 times 10 to the Q1. It says 1, and then there's a symbol microcoulomb. 1. What's micro? It's on your formula sheet. Is it 10 to the negative 6? Yeah, you can just replace every micro with a 10 to the negative 6 on your scientific notation button if you want to. Q2 is also 1 microcoulomb, reading from the picture. All over, not 20. Why can't I use 20 centimeters? So 0.2 squared. 9 times 10 to the 9th. Type this in on your own. I get 0.225 units, Aiden. It's a force. Direction. Which way is charge 2 feeling a force from charge 1? Is charge 2 being pulled towards it, left, or repelled away, right? Well, are they like or unlike charges? So right now, ignore charge 3. Pretend it's not even part of the picture. Sorry? They're unlike, so unlike charges will attract. So what direction is charge 2 feeling a force? To the left or to the right? Now we repeat. But this time, we're going to do the force between charge 2 and charge 3. Now, there is also a force between charge 1 and charge 3. Who cares? The question, Eric, didn't ask that. It wants the net force on charge number 2, the positive 1 microcoulomb charge. So it's going to be 9 times 10 to the 9th. Charge 3, 2 microcoulombs. Charge 2, 1 microcoulomb. All over 0.1 squared. You can probably backspace and edit and just change some of the numbers. I'm willing to bet. I just need to change that 1 to a 2. And I need to change that 2 to a 1. I don't know what I get. Get 1.8? It's closer and bigger, stronger force. Okay. Ooh, Nicole, which way will charge 2 feel a force because of charge 3? Are they like or unlike? So they will attract. So charge 2 will feel a force in which direction because of charge 3? Okay? They're going to attract, right? So which way will this feel a force? Yes, don't overcomplicate it. To the right. How will I add 1.8 right and 0.225 left? Winner minus loser. Who's right? So final answer. It'll be 1.8 minus 0.225. 1.575. I'll go to 4 sig figs. Newtons. What direction, Nicole? Right. Right. Last one. At which point, approximately, could we place a positive 1 microcoulomb charge so that it will experience no net force? Choose A, B, C, or D. I'm going to just try each of these. Don't write this down, but look up. So it's asking, if I put a positive 1 charge, where will it experience no net force? My first thought might be right there. I'm going to cover this charge up. Which way will a positive at location A feel a force because of charge B? Will it be attracted to the right or will it be repelled to the left? Well, what's the charge at location B, Ella? Positive or negative? So are these like or unlike? Unlike charges attract, it'll get pulled to the right. And now I'm going to cover this charge up. Which way will a positive feel a force, Ella, because of this guy? Well, is this charge negative or positive? Are they like or unlike? So it's also going to be attracted to the right. Can to the right plus to the right ever equal 0? We'll cancel out there. And I think I can make a similar argument at location E. If I put a positive there, I think it's going to get pulled to the left and to the left. In fact, where do you think it might be? Either which two letters? Where do you think the force might cancel out? Which 2 letters are looking likely? B or D. So let's put a positive right here. Eric, this would get pulled to the left. This would get pulled to the right. Oh, but wait a minute. It's further away, so it would be weaker. Oh, but it's a bigger charge, so it would be stronger. Compare that with right here. It would get pulled to the left, but we're further away and it's a smaller charge. We would get pulled to the right harder because it's bigger and we're closer. Yeah, I think it's definitely B. It says explain your answer using appropriate physics concepts. Oh, and I didn't even look at C. By the way, the force on C, it looks like it would get pulled this way and this way. How would you add those 2 directions together? Draw them. You could find the direction there by adding those 2 vectorially. I think it would get pulled a little bit to the right and a little bit down, but I don't know. Okay. What's your homework? You can try number 1. Try number 2. Try number 3. 5 is good. And then 6, 7, 10, I skipped 8, 11, 12. Oh, we got more, Mr. I'm probably going to skip 14.